Welcome to the course analysis of several variables, and this is the module 3 part 1 where we are going to discuss about the differentiability of several variable functions. So the this chapter have this module have two section. One is the first one is the differentiability, and the second one is the chain rule. Differentiability of several variable function is defined as follows. So for first we will take that omega be an open ball on Rn, and then let's A belongs to a point in the omega, and where we are going to define the differentiability of the function, and f is a function from omega to Rm. Then the differentiability of this function f is defined as follows. Let's say f is differentiable at the point x is equal to a if there exists one function epsilon from b0 r to rm and a linear mapping a from Rn to Rm. So here b0r is open ball center at 0 and radius and there exists a linear mapping A from Rn to Rm such that f of a plus h is the function f a plus h can be re-expressed as f of a h absolute value of h epsilon h, and if we can write that and we follow these conditions that epsilon h will tends to 0 when h is tends to 0, or some cases we write absolute value of h tends to 0, then this functions f will be differentiable. So we need, okay, now we try to give few notes about these notations. The first thing is that we are saying that f of a plus h will be expressed in that form in the previous slide. But the first question arises that is f of a plus h is well defined. So let's see that. Now if a belongs to omega and the set omega is open, so then by definition there exists a ball center at a with radius r such that x belongs to Rn and mod of x minus a less than r. This is a subset of omega by the definitions of the openness of omega. So this set, this ball should be belongs to the set omega. Now let h belongs to be 0r, as we say that we need that h. Then absolute value of h we can write it as a plus h minus a. Just add a and minus, which is less than r, because h belongs to b0r. So what does it mean? By the same definitions we can see that a plus h belongs to the ball bar. So therefore f of a plus h is well defined because it belongs to omega. The point a plus h belongs to set omega, so therefore a plus h is, so therefore the function f a plus h is well defined. Okay, now if a belongs to linear from Rn to Rm and epsilon h tends to 0 as h tends to 0. Now if a is linear from Rn to Rm exists, then it is unique. Okay. So there is only one linear functions is from Rn to Rm if it is exist, and that linear functions is actually will gives you the derivative of the functions at the point A. It will be same as the functions derivative in the point. Now if it is differentiable, f is differentiable on omega if it is a differentiable at every x belongs to omega. So we defined before that is only a particular point A. Now it is for all point at the omega. Then the new functions means f dash will be a functions from A and linear Rn to Rm, means the domain of this range for this linear functions will be the range of the function, and that is defined as x is a functions f dash. Okay, so this is about the few facts on the differentiability of functions. Now we have an examples here that prove that f r into r is defined by fx equal absolute value of x whole square. X dot x is differentiable on Rn, and we need to find f dash x. Solution. So let h belongs to Rn, then f of x plus h, this is equal x plus h. The distributive properties of the dot product, we can write it here, x dot x plus x dot h plus h dot x plus h dot h. So this is equal x dot x, which is the given function fx, plus x dot h, so we can write it to x dot h plus h dot h, which is absolute value of h whole square. So this is equal f of x plus a h plus absolute value of h epsilon h. So where ah is equal to x dot h and epsilon h is equal absolute value of h, because this absolute value of h whole square we separate it as per our requirement, absolute value h multiply epsilon h, so epsilon h is equal absolute value of h. Clearly epsilon h is equal absolute value of h tends to 0 as absolute value h tends to 0. So this condition is satisfied. Now we are left with that AH is linear. So next we'll show that AH is linear. So AH is equal to x dot h. So let's h1, h2 belongs to Rn and alpha belongs to R. Then A h1 plus alpha h2. So this is by definition it will be 2 x dot h1 plus alpha h2. Now again, by the distributive properties of the dot product, we can write it here to x dot h1 plus alpha x dot h2. So this is equal to x dot h1 plus 2 alpha x dot h2. So which is, this is together we define as a h1 plus alpha a h2. So this implies a is linear. Okay, now this question asks that find f dash x. So we will find this f dash x after some slide. But we'll note it here that it will be this 2a x dot h because of this remark. This one. Because of this one, so we can say that f dash ah is equal this 2x dot h. Okay, now we have a theorem here, and which is a general theorem and true for any differentiable function, that if it is a open ball on Rn and a belongs to omega and this function is defined, then f is differentiable at a, then it is continuous. So this is like the calculus 1 single variable function, that every differentiable function is continuous. So this is also that same condition, that every differentiable function is continuous on Rn. Okay, this is another criteria for the differentiability of function, constant function. So okay, so this theorem gives us the differentiability of a constant function. So if f is differentiable on omega and for every x belongs to omega, f dash x is equal 0. So 0 is a 0 functions from Rn to Rm. That means h from Rn will goes to 0 of Rm. So to be specified, we can, this is 0 of Rn will goes to 0 of Rm when f is a constant function. Now here is another interesting characteristics, that every linear function. So this is the condition that function should be linear. If function is linear, then f is differentiable on Rn, and for all x belongs to Rn, f dash x is equal f. The functions have the same derivative. The linear functions derivative will be same as the function. So how this part, to understand it, we will take one example. Okay. Let f is from Rn to Rm, defined as fx is equal a dot x for some fix a belongs to Rn. Now from here we have that it can be shows that, okay, we can show easily that f is linear. You can just take fx plus lambda y and the distributive properties of the dot product, these functions will be linear. Okay, now so therefore by this theorem, so by this theorem we have f dash x on h is equal f of h. So since f dash is a function from Rn to Rm, so we take one h belongs to, so for all h belongs to R. So this is equal a dot h. Okay, so now we have another interesting definitions of the function. So it says that let omega be an open ball in Rn as usual in R. So here is the function is from R and f is from omega to Rm. Then f is differentiable at A if and only if fi is from 1 to m are differentiable at A and f dash A is from R to Rm defined as f dash h f dash A. So here is the interesting part is that how to, so let's explain this theorem. So f is here omega which is subset of R to Rm. So therefore here is t is single variable and this is will be f of t. So f of t will be, because it is on Rm, so you will have here f1t, f2t, fm t. The m component will be there. So this f is differentiable if each f1, f2, fm are differentiable, and the function f dash a will be, so f dash a is equal f1 a, f1 dash a, f2 dash a, and fm dash a. So this is the general definitions, but since it is a function, so we have to take this function on operating on h, then in this case it will be multiplied by h. So let's have one simple example. f of x, f of x is defined as, let x cosine x and e to the power x square. So in this case, note that the function is from f r to r2. So the function is differentiable if each of this component is differentiable. So this is differentiable, this is differentiable. So f is differentiable at any x belongs to R as x cosine x and e to the power x square are differentiable. So therefore, and f dash x operating on h is equal the derivative of the first component, which is cosine x plus cosine x minus x sine x minus x sine x multiply h and 2x e to the power x square are going to discuss the second part of the module 3, which is chain rule of functions on Rn. So in this case, so let's have the definitions of the chain rule. So we have here that omega be the open ball in Rn, and small omega is an open ball in Rn. So we are defining functions from f omega to omega, and g is from omega to rk, and those functions are differentiable. So if a belongs to the omega, then the g composition f is a functions from omega to r to the power k is differentiable, and it is given as g composition f dash a is equal g dash f a multiply f dash a, and in particular if we have a h here, then this will gives you g composition f dash a h, and this is given by this formula. So this is the basic definitions of the chain rule. Now we'll try to solve some numerical problems using this chain rule. Using chain rule, we will prove that this function f from R2 to R is defined as fx square y, which is differentiable at xy belongs to R, and xy belongs to R2, and f dash xy, and we will find that derivative of f x y. So to do this, we will divide these functions in three parts as a combination of three linear function, and then we'll solve it. So let's define three operator. Solution. So define three operator here. L1 from R2 to R defined by define as L1 xy is equal x, and then we define L2 from R2 to R define as L2 xy, this is again x, and then L3 from R2 to R defined as L3 xy is equal y. F is equal L1 multiply L2 multiply L3. So we are going to use this product rule to find the derivative of this function. Now L1, L2, L3 are linear functions from R2 to R, and they are differentiable. So this implies f being the product of three differentiable function, it is differentiable. Okay, so we got the conditions for the differentiability. Now, what will be the differentiation of these three functions? So now, for that h is equal h1 h2 belongs to R2. Then, since L1 is linear, so we'll have here L1 dash xy operating on H is equal L1H is equal H1. By similar way, L2 dash xy operating on H is equal L2H is equal H1, and L3 dash xy H is equal L3H, which is equal H2. So we got the derivative of these three functions. So now we'll apply and find the derivative of f dash x y. Okay, so from now we have here, so this will give us now, therefore f1 dash xy operating on h, this is equal L1 dash xy on h, L2 xy as it is, L3 xy as it is, plus L1 xy, L2 dash xy operating on h, L3 xy plus L1 xy, L2 xy plus L3 dash xy operating on h. So this will gives us that L1xy, we already calculated it, which is h1. So we'll get here h1. L2xy, which is defined as x. So L2xy is x, and L3xy is y, plus here L1xy is x, L2xy is again h1, and L3xy is y, plus L1 is x, L2 is x, and L3 is L3H is H2. So this will gives us 2 xy H1 plus x square H2. Okay, this concept can be generalized further, and in the sense that we can have let's the function is maybe like this, let g x y and g, this is equal x to the power 500, y to the power 1000, z to the power 90. So you can just have the derivative in the form of the product rule, and then you can do that, because x to the power 500, so we cannot write 500 linear operator to solve this problem. So therefore generalized formula of this one, g dash x y g. So here you will see that g is from R3 to R. So therefore we can take h as h. So h belongs to R3, h is equal h1, h2, h3. So therefore this derivative will be 500 x to the power 499. Remaining will be as it is, z to the power 90 h1 plus 1000 x to the power 500 y to the power 999 and z to the power 90 h2 plus the last one is 90 x to the power 500 y to the power 1000 z to the power 89 h. So we can generalize the whole idea in this. Next section is about the application of the chain rule to solve numerical problems, where we are going to solve few numerical problems using the chain rule. Okay, so our first problem is that prove that f r2 to r, which is defined as this complicated function and is differentiable, and we have to find f dash. Let's start to solve this question. So we will try to take this function as a product of two functions and make it simplified in this form, and then we will solve it. So we take it two function. So let gxy is equal e to the power x y square, and then we define g1 xy is equal x y square, and g2xy or g2t is equal e to the power t. So you can see that here g1 is a function from r2 to r, and g2 is a function from r to r. So clearly g is equal g2 composition gy. In this case, if we see that g2 and g1 are differentiable, then the composition function is differentiable. So now g1 xy is differentiable as it can be written as product of three linear functions like as L1 x is equal x, L2y is equal y, and L3y equal 1. And since linear functions are differentiable, so the product of three linear functions will be differentiable. And G2t is a single variable and clearly differentiable. Therefore, G is equal G2 composition G1 is differentiable. Now G dash X H. This is equal, by definition, G2 dash G1 now let H is equal H1 H2 belongs to R2, then G2, then G dash XY operating on H is equal G2 dash G1 XY and then G1 dash XY operating on H. So this is equal, so G2, the derivative of G2 is e to the power t, so therefore it will be e to the power G1 XY and then G dash XY. So G dash XY is G1 XY is, so derivative of X, so this is Y square H1 plus 2XY H. So now just substitute e to the power X Y square H1 plus 2XY H2. Let note it down, this is as 1. Now we'll take another function mxy. So let mxy is equal square root of 1 plus 2x square plus 3y to the power 4. So in this case, we take another two function m1 xy is equal 1 plus 2x square plus 3y to the power 4. m2t is equal square root. By similar logic of the polynomials and power of the polynomials, power of the variables, clearly m1 is differentiable as a power of variables and m2 being m2 is also differentiable. So therefore m being the composition of two differentiable functions is differentiable. So therefore, for H is equal H1 H2 belongs to R2, M dash XY H is equal M2 dash m1 xy and then m1 dash xy writing on h. So this is equal square root t is 1 over 2 square root of m1 xy multiply. Now m1 is this one. So the derivative of m1 with respect to x, it will be 4x. And when we do the derivative with respect to x, the component will be h1 plus with respect to y, it will be 12 y to the power 3 h2. So now substitute the value of m. So you will get it here 4x h1 plus 12 y to the power 3 h2 over 2 square root of m1 is 1 plus 2x square plus 3y to the power 4. So this is we can add as. Next is the consider the given function f. So now note that f of xy is equal g of xy multiply m of xy is differentiable being the product of two differentiable functions. And the product is given as f of xy h is equal g dash xy h mxy plus gxy m dash xy h. So therefore g dash xy, which we already calculated, the first equation, which is this one, e to the power xy square y square h1 to xy h2, e to the power xy square y square h1 plus 2xy h2, and then we write the m. So what is m? M is given as square root of 1 plus 2x square plus 3y to the power, and then we have g here plus g is given as e to the power x y square, and then the derivative m dash xy h. So this m dash xy h is this one 4x h1 plus 12y to the power 3 h2. So 4x h1 plus 12y square h2 over square root of 1 plus 2x square plus 3y to the power this y cube. So this is after simplifications of h1, h2, we can have the final answer. So we can write it here. Let's say y square e to the power x y square plus 4x e to the power xy square over square root of 1 plus 2x square plus 3y to the power 4 h1 plus 2xy e to the power x y square square root of 1 plus 2x square plus 3y to the power 4 and here plus 12 y to the power 3 to the power xy square over square root of 1 plus 2x square plus 3y to the power 4 h2 is the final answer. Let's move to the our next problem, that a is a linear function from Rn to Rn and b is from Rn, and we define a function f Rn to R as f of x equal ax plus b whole square power 2. So first thing is that so that f is differentiable by definitions and find f dash. So let's have the solution for this part. So we have to show that to show f is differentiable, we have to show we need to prove that f of x plus h is equal to f of x plus th plus absolute value h epsilon h, where t is linear and epsilon h tends to 0 as mod of h tends to 0. Okay, so we start with this, and this is for all h belongs to Rn. So let's start with this f of x plus h. This is by definitions is equal a x plus h plus b whole square. So this is equal ax plus ah plus b whole square. This is because a is linear. This we can write it as this is equal ax plus b comma ah dot ax plus b ah. So we extend this dot product, we can rewrite this. This is equal ax plus b dot ax plus b plus 2 ax plus b dot ah plus h dot ah. So this is equal absolute value of ax plus b whole square plus 2 ax plus b dot ah plus ah whole square. So this is given function f of x, and this is we denote it as th, and the last one we write it as absolute value of h epsilon h, where th is equal to ax plus b dot ah, and epsilon h is equal mod of ah whole square over absolute value of h. Now we are left that t is linear and epsilon h tends to 0 as h tends to 0. Okay, now epsilon h is equal absolute value of ah whole square over absolute value of h, clearly greater than equal 0, and further mod of ah is less than equal norm of a absolute value of h implies epsilon h is less than equal norm of a whole square absolute value of h whole square over absolute value h, which is norm of a whole square absolute value h, and clearly tends to 0 as absolute value of h tends to 0. So therefore altogether we have epsilon h tends to 0 as mod of h tends to 0. And now the next part is th is equal to ax plus b dot ah is linear as a is belongs to L Rn to Rn. But if you want to prove that also, you can prove it in this way, that H1, H2 belongs to Rn, alpha belongs to R. So therefore T H1 plus alpha H2 is equal to Ax plus B dot A H1 plus alpha H2, which is linear because A is linear. So we can write it AH1 plus alpha AH2. And the distributive property of the dot product, we can write it here to AX plus B dot AH1 plus alpha to AX plus dot AH2. So this is equal T of H1 plus alpha T of H2. So therefore T is linear. So finally we'll have, so therefore T is linear. So finally we conclude that F is differentiable. Dash X H, this is will be as the TA is the linear function, and then this is equal to AX plus B dot A. Okay, now next part is that we say that if f dash x equals 0, if and only if x is equal minus A inverse B. So to prove that, we have to first consider the A. Since A is belongs to L, Rn to Rn, A is bijective. So for any V belongs to Rn, there exists H belongs to Rn such that AH is equal B. Okay, H. Okay, so as in the shown in the previous slide, so H is equal V. Then we have, so f dash x is equal 0. So this implies f dash x operating on H is equal 0. So this is equal to ax plus b dot ah is equal 0. So this implies to ax plus b dot v is equal 0. Since v is arbitrary, we must have ax plus b is equal 0. This implies ax is equal minus b. So this implies x is equal a inverse minus b is equal minus a inverse b. This is because as a belongs to L, Rn to Rn implies a inverse belongs to L, Rn to Rn. So therefore we prove that x is equal minus a inverse. Now the last part of this question is that we have to show this gx is differentiable. So for that we took two functions, that f of x is equal ax plus b whole square, which is differentiable as proved in part A. Okay. Now this will gives you gt is equal ln 1 plus t square is a single variable function and clearly differentiable. Okay, so now what about g? Okay, so this is not g, this is m, so empty. So what is g? So therefore g of x is equal m composition f x is differentiable, being composition of two differentiable functions. Okay, so now what is the differentiation? So g dash x on h, where h is from Rn, this is equal m dash f of x and f dash x on H. So this is equal to m dash. So m is this. So m dash differentiation is 2 f of x over 1 plus f of x whole square, and f dash x h we already calculated. So this is equal multiply 2 ax plus b dot ah. Now we substitute fx and then we will get the final answer. So this is equal to, this is ax plus b absolute value whole square over 2 over 1 plus 2 absolute value of ax plus b to the power 4, and then 2 ax plus b dot ah. So this is the final answer. So e to the power g1 xy e to the power g1 xy. So e to the power g1 xy is xy square. So e to the power x y square h1 plus 2xy h2. So this is the first derivative.